In this video, I'm going to import some Python libraries to sort of just look a little bit more at a simulation I like, the snake eye simulation. So I'm going to simulate the rolling of two dice, and I'm going to continue to roll them until I get both dice to be ones, which is snake eyes, and then I will count how many rolls that took, and that will be sort of like one one thing and one sample, and then I will take many samples. So I will do that repeatedly. And then I'm going to sort of just create a big list of all those number of times it took to roll snake eyes, and then do some statistics. And the emphasis here is on the libraries. So I think I've done something before where I've done the simulation before, and so that part will be repeated, but then the new stuff is the libraries. Okay, so I have random. I always had random because I'm using it in the simulation to simulate the rolling of two dice, but I'm bringing in the matplotlib. I'll call it scipy and numpy. And if you don't have these, then you may need to down in your terminal. If you don't have a terminal, get a terminal. But you might have to run in the terminal, pip install in the library. And matplotlib was giving me some problem. I thought I had it, but it was giving me a problem. And then I tried to install it again, and that was giving me a problem. But when I added -- user, the option, it went through. Okay. And it may be this, so I had to install matplotlib and scipy. I did not have to install numpy, but I think I had used it before, so that may be why I didn't have to install that. But if you need to install that, then you might need similarly pip install numpy or -- user numpy. Okay. So I'm going to run. It turns out that this simulation, the results are going to sort of be follow what's called a geometric probability distribution, which has a very long tail. And so if you want to sort of compare yourself to the theoretical results and have anything good, then you need a lot of samples that really probe that long tail. And so that was 17, and then 18 is just my initially empty list of results. In main here, I'm going to have a for loop going over the samples, and I'm going to call a function defined below, count to snake eyes, and that's going to return the number of times of rolling to get snake eyes, and then I'm going to add that to my snake eyes list up here. So let's scroll down here. I am setting the roll count to 0. The number of times I've rolled started off at 0. Start the two dice at some values that all it really matters is they're not both ones. And then I start a while loop. And while the sum of the two dice is not equal to 2, I get a random die 1, a random die 2, and increment my counter. And then I'll be testing the condition when it's all done. When I'm finally out of the while loop, then I return my count. So, and then down at the very bottom, I am calling my main function. So back to my main function. So this far by 26 or 27, when I get out of that for loop, I will have completed my simulation. Then I'm doing the skew and kurtosis. So those are two distribution measures. So I'm just like average. There's like other statistical measures, more basic ones. The average, of course, the median, the standard deviation, and variance. These two, the skewness and the kurtosis, are sort of like are based on like higher moments, and so the skewness is based on a third moment and tells you sort of is your distribution sort of evenly distributed around some average, and kurtosis involves the sort of the fourth moments and sort of really gets out into the tails of a distribution. Okay. And this was so I could just ask for the skew and the kurtosis, and that was using the scipy. So it had those statistical measures. Okay. And when we look at the results, which will be printed out when if I run it, so let me run it, and then we can just run it again if we want more. I'm doing, I think it was 100,000, so it takes a little while to do the simulation, but not too long. And then here is the skewness and the kurtosis. And then I made a histogram. I made a different version of a histogram. I made a box and whiskers plot. And then I generated a geometric distribution, which should be pretty much the same as my simulation. Okay. And I didn't generate it. I used a library that generated it, I should say. Okay. So the skewness, here's a formula for the skewness that I have a video that then talks about Wolfram Wolfram Cloud and Mathematica that sort of, in some sense, derives these results. So for the skewness and the kurtosis, and just while we're talking about kurtosis, like if you were in Excel and you did a kurtosis calculation, that would be the excess kurtosis, where you sort of subtract off 3. But this, what scipy did is not excess kurtosis, but just flat out kurtosis. And so it's not like the version of kurtosis in Excel. Okay. So that was the skewness and the kurtosis. Okay. Then I'm making a histogram. So I'm using matplotlib here and making a histogram of the snake eyes data. The bins in a histogram, let's run this again so I can sort of point. So the sort of the bars in a histogram, sort of how wide they are, that is the bin. Like so I have various bins, and there's a parameter and says something about the bins helps you sort of, you can just you can forget the parameter and it will do something automatic, or you can, if I just have a number, then I'm saying how many bins I want it to have. Or you can sort of put like a list in here and say, here are, the bins I want. And I can do a color and I can do more, and then I can give it a title and show it. Okay. So that is the first one. That is the snake eyes histogram. There's the title. They get pretty small. And a histogram is sort of how many times something happened. So this first bin, about 50,000 of them occurred in this first bin, and so on down. Okay. And then this is sort of modal. So it's sort of like the program is sort of stuck here. And then with this show, and then if I close this, it will move on. And now it's making, I'm still in matplotlib. I am same data, same number of bins, but I've added a density true, and I changed the color to orange. And density true, now the y-axis here is a we're dividing by the number of samples, and we're also scaling the bin width, and this becomes like a probability distribution. So this is closer to mathematics, where they sort of uh, integrated area over this would be 1. So that's a useful parameter for if you wanted to compare this to some mathematics when you're playing, the mathematics is more about the probability distribution rather than a histogram. A histogram will be dependent on what you choose your bins and how many samples you happen to have. And then this probability density, this density equals true parameter, get you more in the realm of like probability and statistics, where you can sort of compare yourself to some math. Okay. And then again, I gave it a title and a show, which is modal. So if I close this, it will move to the next one. And then I'm making a box plot of the snake eyes data. So this is this square, sort of the box, that sort of rectangle. It's not a square. The bottom represents the sort of the first quartile. The top represents the third quartile. This flat line at the bottom represents the minimum. The orange line, I'm going to say, is the median, but might be the mean. And then there is a definition in a distribution of outliers. So this top line is the division in this case. In other distributions, it may be the maximum, but in this case, it is the dividing line between the definition of what are outliers and what's not an outlier. And then all these circles represent outliers. This is a distribution that has a very long tail and lots of outliers. It's just the nature of this simulation and distribution. It's a geometric distribution. Okay, so show that, and then I'm going to, again, modal, so close it. And now I'm going over to the numpy library, and it has some distributions built in, and this guy is a geometric probability distribution with a p. There's only one parameter in that, and it is the probability. There's, if you consider the rolling of snake eyes a success, then the geometric distribution is you have some number of failure. It's the probability of your first success. So first time I roll snake eyes, and so this is the probability of success in that to get the actual snake eyes. And that's the only really parameter in the distribution. And then this is just, and I wanted 100,000 samples. So, and then it's generating this distribution for me. Okay. So I'm not running through the simulation with my while loop and doing random numbers. It's going directly to the heart of the matter, that this is a geometric distribution. And so it's much more efficient than my dice simulation. Okay. And then I did the kurtosis and the skewness and the kurtosis again, and another histogram. And I did the density one, so this should look an awful lot like the one for the simulation, because this is the distribution for the geometric distribution is the distribution that applies to this snake eye simulation. Okay, that's all I wanted to show. Just some fun with the libraries that are in Python for doing some statistics. So I was using matplotlib to do, of course, the plot. I used scipy for these skewness and kurtosis, the sort of like third things related to the third and fourth moments of the kurtosis, and then numpy was had the geometric distribution built into it, and they're known. This is although it's got a very long tail, it is and very easy mathematically to derive results with. It's a very sort of easy distribution because it's related to like a geometric series. So everything's highly summable, and so you can get exact probability results to compare with your simulations. Um, it has that long. The geometric has that long tail, and the kurtosis is very sort of, I don't know, tail probing or measurement. And so that was why I was all the way up at like 100,000 samples to have some hope of getting the kurtosis right, or at least in the right ballpark. All right, that's it for this one. Thanks much for your attention.